right, today's topic is optimization. This is a staple in any differential calculus book or unit. This is basically an applied, meaning it's a model, it's a word problem. It's an applied, absolute, extreme problem. So it's a word problem where you're trying to find the absolute possible min or max value from some quantity. And these are the 4 steps that you're going to want to use. And you want to make sure to get these copied down, and I'll explain more what they mean, like what this clue is and things like that. But we want to come up with an equation, we want to eliminate a variable, we want to take the derivative and find critical values, because we've learned that extreme values happen at critical values, maybe at endpoints, but usually at critical values where our derivative is 0 undefined. And then we're going to use those values to determine what's the absolute min or max value of whatever quantity it is we're trying to optimize. We're going to start off with a nice simple one, and this is a problem that you probably answered in Algebra 2 at some point, and we'll see why in just a minute, but let's just follow our steps. We're going to start by writing an equation for the quantity, in this case, that's being minimized. So let's get a little picture. A lot of times a diagram is good here. There's always a farmer and a rancher in this chapter of the book because of this type of question. We want 2 adjacent rectangular corrals, and in this case we want them to each have an area of 2,000. So there's infinitely many ways you could arrange this. They could be tall and skinny, they could be short and wide, they could both be perfect squares. But one of those will minimize the total feet of fencing used, and that's what we're looking for. So the thing we're looking for is the dimensions, and you could do, I'm going to call it y here and x here. I'm going to use the dimensions of 1 corral. That means I need to build 3 fences of length y and 4 fences of length x. And there's no reason you can't arrange those variables how you want them. You could have called this whole length down here x if you wanted to. It'll just change the way we approach the problem. But I think it's going to be easiest to have 4 sections that we call x and 3 that we call y. So now let's write an equation for the quantity to be minimized. I actually, in calc, was required to write the word minimize just to drive home what we're doing, and I still remember it to this day, so it's probably a good idea. We want to minimize the feet of fencing. So now I'm going to write an equation for the amount of fencing. In its simplest terms, the amount of fencing I have is 4x plus 3y. If you remember, step 2 is to use the clue to eliminate a variable. I don't want to take a derivative with x and y both. I want one independent variable, and that's either the length or the width of these corrals. So I'm going to use what's called, this is not a common term, but I'm going to call it the clue. And in our case, the clue is that each corral is 2,000 feet squared. It might also be known as like a requirement or a parameter or something like that. I like clue. My clue is that xy is 2,000. That would make each rectangular corral have an area of 2,000 square feet. Now I can eliminate either x or y. I'm used to x being on the right side of an equation, so I'm going to solve this for y, which tells me y is 2,000 divided by x, and I'm going to substitute that in to my fencing equation and get 4x plus 3 times 2,000 over x. So this is the equation that needs to get, this is the expression that needs to get minimized, and I can simplify it just a little bit. 4x plus 6,000 over x. And if I can find the absolute minimum value of this, then I've found the least amount of fencing that will get me the proper 2,000 square feet each. So how does that happen? Well, we take the derivative and set it equal to 0 and see what we get. So the first derivative, f prime, I haven't taken a derivative yet. I've only simplified the function for fencing. The derivative is 4 minus, so let's think of this over on the side. 6,000 over x is the same as 6,000 x to the negative 1. The derivative of that, if we drop the negative 1 down, is negative 6,000 x to the negative 2, or 6,000 over x squared. Okay, so move up here. This is going to equal 0. At my critical points. I'm going to move that 6,000 over x squared to the other side of the equation. I'm going to add it to both sides of the equation. And now to solve, essentially I'm going to divide both sides by 4, multiply both sides by x squared, and I'm going to get 6,000 over 4 is 1,500. X is the square root of 1,500. So the square root of 1,500 is about 38 point something. Let me check my calculator. It's 38.7. Let's call it that for now. Now this is the only value where my derivative was equal to 0. Critical points can also happen when your derivative is undefined. That's a point we would need to check. But if our derivative was undefined, it would have been because x equals 0 right here. And let's think about in the real world, we're not going to have x equals 0. That would be just 3 infinitely long fences set next to each other. If x is 0, that's because y has become infinitely large, so that doesn't make any sense. So 38.7 is our only possible value that makes any sense. And since y is 2,000 divided by x, 2,000 divided by the square root of 1,500, or divided by 38.7 is 51.6. So my final answer, x is 38.7, y is 51.6. That's the smallest amount of fence, or that's the dimensions of the smallest rectangular corral that will guarantee 2,000 square feet. All right, so here's one that's a little bit more complicated as far as the equation goes. It's another classic example. We're making tin cans, and we need to make a cylinder. The requirement is that the volume must be 200. We're in everything in centimeters here. The top and the bottom material of the can cost 12 cents. Maybe it's a little bit thicker metal or something. The outside, the sides of the can, the main part of the cylinder, not the top and bottom, that's only 9 cents per square centimeter. So there's a certain tin can, it might be short and fat like a tuna can, or it might be a tall skinny can. Some combination of radius and height of this tin can is going to be the cheapest can we can make. And if we are, in fact, tin can manufacturers, I promise you we want to know what's the cheapest tin can we can make that will still have 200 cubic centimeters. So I've gone ahead and written an equation for the quantity to be minimized, and that's the cost. So the top and bottom are each a circle, pi r squared. There's 2 of them for top and bottom, and it's 12 cents each. So whatever that area is, I need to multiply it by 12 cents to get the cost of making the top and bottom. The sides of this can are actually, if you were to slice this thing and unroll it, it's just a rectangle. But the length of that rectangle is the circumference of the circle. That is 2 pi r, and the height of that rectangle would be the height of the can. So 2 pi rh, that's the area of the outside edge of the cylinder, times 9, because it's 9 cents each. So it's important that you can get this equation for cost, and I know I did, without writing it all down during this video, some stuff in my head, but make sure you understand why that is the way it is. Now we're going to move to the clue. We've got radius and height both in this equation for cost, and I don't want them both to be there, so I need to get rid of one. One of my terms just has radius in it, so I want to try to get rid of height. That would be an easier substitution. If I can solve for height, it's 200 divided by pi r squared. I can sub 200 over pi r squared in right here. All of a sudden, I don't have h in my equation anymore, and I can work on the derivative. So I'm going to clean up the first term just a little bit and make it 24 pi r squared. And my second term, I'm going to go ahead and put the 2 and the 9 together to make an 18. I've got 1 r there, and now this h is 200 over pi r squared. I want it as simple as it can be before I start worrying about derivatives. So 24 pi r squared is the first term. That's as simple as it can be. I've got an 18 and a 200. That's 3600 pi. Actually, let me get rid of that pi and that pi so I don't have to worry about pi anymore. But I've got 3600 and I've got an r on top and an r on the bottom, two r's on the bottom, so that's a total of one r on the bottom. So just 3600 divided by r is going to represent the cost of the sides of this can. Alright, so now we're ready for derivative. C prime, 48 pi r. When I drop the 2 down and decrease it, remember pi is just a constant. And the derivative of 36 over r is negative 3600 over r squared, for kind of the same reason of the fence problem a minute ago. Alright, so to solve this one, I want to set it equal to 0. I'm going to, at the same time, move the 3600 over, save myself a line. So if I rearrange this a little bit and multiply both sides by r squared, I'm going to move these two r's over here and make it r cubed. And I'm going to divide both sides by 48 pi. So 3600 over 48 pi equals r cubed. So r would be the cube root of 3600 over 48 pi. Now we've gone about as far as we can go with no calculator. So I'm going to pause for just a second, get this decimal, be right back. So that gives me 2.879 centimeters is r. And again, if you were to follow the rules by the book, they would probably tell you to check the endpoints. But the endpoints aren't going to make sense in 99% of the problems. If you get one good critical number, there's a 99% chance that that's your answer. And we'll look at some counter examples to that, but 2.879 is our answer. That's the radius of the cheapest possible can. Make sure you answer the question. They asked what dimensions will produce the cheapest can. Well, the radius is 2.879, but remember, we have a clue that connects radius to height. And let's use this form of it. 200 divided by pi times our answer squared should be the height of the cheapest possible. So sub that 2.879 in right here and see what you get. So if I take my answer and square it, and then I multiply it by pi, and then I do 200 divided by that number, I get a height of 7.678. That is going to be the height of the cheapest possible can. Okay, so we're going to end this one with those two examples, two classics that you'll see in almost every section of optimization in all the calc books. But just remember, this is an applied absolute min or max problem. It's just finding critical points, but the equation stands for something, and that's it.